the weight, we've looked at the tension, and we've also looked at the normal contact force. Let's put this into practice. So here we have a heavy box, okay? We're trying to pull at it with a rope, but it refuses to move, so its acceleration is 0. What are the forces that are acting on this box? What's preventing the box from moving? Let's have a look. So the first force, that's the most obvious one that we've talked about time and again, is the weight. Okay, we draw a really long weight vector because it's heavy, yeah? And because the box is not floating, it's not crashing through the ground either, then I have an equally long normal contact force that's acting perpendicular to the surface, acting upwards, yeah? So that's my normal contact force. Okay, and I'm pulling at it with a rope, I'm pulling it towards the right, so there's going to be a tension force as well, right? There's going to be a tension force. That's my tension force. But we said that the object was stationary, so that means that there must be some sort of force that's acting towards the left. What force could this be? Well, if we were to examine the surface between the box and the ground, right? We were to use a microscope to look at it, it's actually not perfectly smooth at all. There are bumps. And as one bump tries to move across the other, they try to slide past each other, but they have trouble doing so, right? There's a resistance force. So this resistance force along the ground, okay, we call friction. Okay, we call it friction. So friction is interesting because it's always parallel to the surface because it's caused by the bumps in the surface, right? So it has to be parallel to the surface, and it generally opposes motion. Okay, so if you're trying to pull it towards the right, friction will act towards the left most of the time. Yeah. So in this case, our friction is the mysterious force that was acting towards the left, preventing us from moving. But let's say now that you really need to get this box moving, right? So you've asked some of your friends to help. Let's see what happens now. So you're now pulling at the box with your friends, okay, again with a rope. So what forces are acting on the box? The weight remains unchanged. Okay, the normal contact force remains unchanged. Okay, you still have a friction that's acting towards the left. Have friction. Okay, but what's causing the box to accelerate? Well, it has to be the tension, right? Because now you and your friends together are pulling at the box with much greater strength, as illustrated by the longer tension arrow, tension vector. Yeah. So let's see what's happening here. Okay. So got a weight. Okay. So this part of the weight here is trying to cancel out the normal contact force. It does so completely because they're of the same magnitude and they're acting in opposite directions, right? So they've managed to cancel each other out completely. But let's look at the horizontal forces, right? My component of friction here tries to cancel out this component of tension. But it can't cancel it out completely because my tension is much greater than my friction. You see, I'm left with this amount of force here, right? This component of force here. So the component of force that's left behind after all this cancellation of forces, okay, is what we call the net force, F net, okay? You might also have seen this as the resultant force. But let's use F net. It's shorter to right, yeah? So I have this F net here that's moving towards the right. Interestingly, that's in the same direction as my acceleration, right? My F net is parallel to my acceleration. And we'll revisit this concept again in the next video. Okay, so that's the free body diagram for when you pull a heavy box with your friends. Okay, so now summary time. So forces are vectors, okay? They have magnitude and their direction, right? They have magnitude and their direction, okay? Free body diagrams, yeah, they show all the forces, okay? They are represented by arrows acting on one object represented by a dot. So this is my object, and then I have forces acting on the object represented by the arrows. Okay. To draw free body diagrams, You identify and then you draw the forces. Okay, so these forces include the weight, which will always act downwards. You have the normal contact force, N, which always acts perpendicular to the surface. You have the tension T, which always acts in the direction of the string. And you have the friction, F friction, which always acts parallel to the surface and usually opposes motion. So with all of this knowledge, try this practice problem. To draw the free body diagram for this box that's being pulled up a rough slope, so there's a rough slope by the way, by a man. The box is accelerating up the slope. Okay, the box is accelerating up the slope. So try and solve this problem, submit it on the Google form, and I'll see you in the next video.